All right, hi everyone. I'll unmute you for a moment so we can all say hi. Hey everybody.
Hello.
Hi. Hello.
Hope everyone's surviving the pandemic. I'll mute you all again so you can't actually tell me. All right. So today I want to talk about revenue, which is sort of maybe an obvious thing when you think about auctions, but is something that we haven't discussed yet. So we've spent a bunch of time in this class thinking about welfare maximization. In fact, even before we got to the mechanism design section, we defined the price of anarchy and we studied it in a number of games in terms of welfare maximization. Then when we got to the mechanism design section, we considered all sorts of mechanism design problems, starting with things like stable matchings and Pareto optimal exchange. And the underlying goal in all of this was to maximize some notion of aggregate happiness. And we made that explicit when we derived the VCG mechanism, and we proved sort of this powerful theorem that said in a enormously general variety of settings, there's this one mechanism we can run that will always maximize social welfare. But it's not the case that everybody who runs an auction has the goal of making the participants in the auction as happy as possible. Sometimes they want to make money as well, or even primarily. And that's what I want to study in this class and the next class, and actually maybe the next 4 or 5 classes. We're gonna think about revenue maximization. But it's not even obvious a priori, if you think about it for a moment, what that should mean, what our benchmark should be, right? Because when we think about welfare maximization, there's an obvious benchmark. Once everyone shows up to the market, there's some well-defined best alternative we can choose. If it's an auction in which we're giving out items, there's some optimal partition of the items that maximizes social welfare. But given the people that are that happened to show up to my auction, what is the benchmark that I should compare myself to if I want to say that I am doing a good job of maximizing revenue? And so in this lecture, I want to think about this question, and we're going to think about a case study for single item auctions, which is sort of the setting in which revenue maximization is best understood and has the cleanest solution. And we'll talk a little bit at the end about sort of the extent to which the solution we derive today can be extended, and what some of its weaknesses are that we might try to mitigate in future lectures. Okay. So, we didn't remark on it so much at the time, but the VCG mechanism actually was quite remarkable in the sense that it didn't just maximize welfare, on average. In fact, we didn't even need to assume any distribution over bidders in order for it to even make sense to specify what it might mean on average, because it did this much stronger thing. It sort of guaranteed that it maximized welfare on every single instance, right? No matter who showed up to the auction, in the worst case, right, no matter what our instance was, the VCG mechanism was able to maximize welfare on that instance. And so this question of, if we aim to design, say instead of a welfare optimal auction, instead a revenue optimal auction, of what our benchmark should be, is actually a little bit non-obvious. So let's just consider, sort of a the simplest possible setting in which we have a single item to sell and there's only a single bidder that we're going to sell it to. Okay, so we have a wide variety of dominant strategy truthful mechanisms in our design space. For example, we could run the VCG mechanism, but that's probably not revenue optimal because the VCG mechanism, when it's selling just to a single bidder, will always charge $0. So the VCG mechanism won't make us any money. On the other hand, there's a bunch of other stuff in our design space. So one extremely simple mechanism that hardly deserves to be called an auction is just a simple fixed price P, and that just corresponds to the following allocation and payment rule. If your valuation is higher than P, then you get the item and you pay P dollars. If your valuation is less than P, then you don't get the item. Right, so it's sort of the way we tend to price things in stores. We just write down a price P, and anyone who wants to buy the item at that price is able to do so. Okay, so it's sort of immediate to see that these simple fixed price mechanisms are dominant strategy truthful. If I'm committing to some price P, there's no reason to lie about your valuation. And that's true for every P. And so within our design space of dominant strategy truthful mechanisms is one corresponding to every possible fixed price P. And what's the revenue of this class of auctions? Well, if our bidder has value greater than P, then our revenue is P. Otherwise, our revenue is $0, right? We get P dollars if we sell the item, otherwise we get nothing. So, ex post, the optimal revenue obtainable, right, like on a particular instance via any dominant strategy truthful mechanism, of course, is the fixed price mechanism that just sets the price equal to the bidder's valuation. Now, of course, it's only dominant strategy truthful if the price was fixed independently of the buyer's valuation. It's not a truthful mechanism to have someone, walk into the store, report what their valuation is, and then, only then do I sort of turn my back and fiddle around with the price tag machine and price it at exactly what they said. That wouldn't be dominant strategy truthful. But if I had been lucky enough to price the item exactly at what the buyer's valuation turned out to be, well, certainly ex post, that would have been the optimal revenue that I could obtain. But somehow that doesn't seem like a good benchmark. Like, there's no way that I could have known ahead of time what the buyer's valuation was going to be before he walked into my store. And so if we sort of say, okay, well, I'm going to measure the performance of any fixed dominant strategy truthful mechanism by comparing its revenue to the revenue of the dominant strategy truthful mechanism that I get to select after I see what the instance is, we're never going to be able to compete with that. Right, so that's not a fair benchmark. And it's worth remarking that it's a little bit interesting and it's sort of powerful that we were able to compete with this ex post benchmark when what we cared about was welfare. So the way we're going to define our benchmark is in the average case. And to talk about average case revenue, we have to define a few extra things as part of our model to make that make sense. Okay, so previously we never discussed where buyer valuations came from. We just asserted that they existed, and there was no distribution on instances. But now, so that we can talk about the average case, we're going to imagine that there is some distribution on buyer valuations, okay, call it D, and we are going to imagine that buyers draw their valuations independently from this distribution, okay? And the idea is we, as the mechanism designers, at the time that we get to design our mechanisms, we don't know what the buyer valuations are. It wouldn't be fair if we got to design our mechanisms after we learned the buyer valuations, because then we could just set fixed prices equal to the buyer valuations. But we do know what this distribution is. Okay, so we get to design our mechanism as a function of this distribution, and our goal is now going to be well defined. We're going to want to design the mechanism that obtains the highest revenue on average over instances drawn from this distribution. So for a single item auction, if we want to commit to setting a fixed price, in this framework, we can now perform an easy calculation and figure out what is the fixed price that's going to maximize our revenue. Right, so let's just sort of walk through that calculation just to get ourselves comfortable with this setting. Okay, so suppose I set a fixed price P. What's my revenue going to be? Well, there's two cases. Either the buyer decides to buy the item, in which case my revenue is P, or the buyer decides not to buy the item, in which case my revenue is 0. And so my expected revenue, my average revenue, is just P, the price that I set, times the probability that the buyer wants to buy the item, times the probability that the buyer actually has a valuation that's greater than P. Okay, so we can write that down in terms of the CDF of this distribution, the cumulative distribution function, which in this case I'll just write as capital F of P. And remember, the CDF of a distribution is just the probability that a valuation drawn from the distribution is less than the price P. Okay, and so the probability that a buyer who shows up randomly drawn from this distribution would like to purchase the item that I price at P is just the probability that his valuation is greater than P. So it's 1 minus F of P. And so my revenue as a function of P, I can just write down as P times 1 minus F of P. Okay, so this is some closed form expression for revenue. And if I have an expression for the cumulative density function, CDF, of my distribution, then I should be able to just pick the value of P that optimizes this. So, for example, suppose my value distribution is just the uniform distribution on 0 to 1. So, a new buyer has a value function, a valuation for the item that is uniformly random between 0 and 1. Well, then my CDF, F of P, is just equal to P. The probability that a randomly uniformly drawn valuation is less than P is exactly P. And so my expression for revenue is just P times 1 minus P. And if I want to maximize that over my choice of P, I can do some simple calculus or just sort of observe the shape of the curve. And notice that the price that maximizes my revenue is 1/2. Okay, if I set my price equal to 1/2, then the probability that someone wants to buy the item if their valuation is drawn uniformly at random, well, that's just 1/2 as well, the probability that their valuation is in the top half of the interval. And when they do buy the item, I make exactly $1/2. And that means I can obtain revenue 1/4. And it's not hard to see that there's no other fixed price that will make me any more money than that. Okay, so this is called the monopoly price for the item. So, we're gonna quickly move to a more complicated setting than this, but it's gonna be in the same basic framework in which we have an underlying distribution that we're assuming valuation functions are drawn from, and we're gonna perform some kind of optimization where the thing that we want to maximize is our expected revenue. So let me just stop now and ask if there are any questions, because if there are any confusions about the model, the role in which the distribution is playing, it's a good time to ask them now before we sort of move on to anything too complicated. So any questions about the setup here, or what the goal is, what we're trying to do, or why the expression that we have on the slide here corresponds to our expected revenue in this setting? All right. So the case when there was only one bidder, that was pretty easy. Let's think about how we might begin to address the case when there are many bidders, because now we're going to have to design a more complicated object. When there was just one bidder, we could just sort of fix a single price. But remember, we still only have one item. So if there's many bidders, we can't just fix a price. We really have to come up with an entire auction format, like a whole mechanism, because at a single price, there might be many people willing to buy the item, and we need to figure out some way to break ties. And somehow we should be able to do better than just having a fixed price. If we have more than one bidder, we should have some mechanism that allows competition somehow to drive up the price. If there's many people willing to buy the item at some price P, then there should be some way for me to make more than P dollars. And so we can think back to the machinery that we've developed around mechanism design. And we want to remember that the thing that we want to design, right, it's two things. It's an allocation rule, X, paired with a payment rule, P. And we need to be able to design X and P so that the mechanism is dominant strategy truthful, dominant strategy incentive compatible, because we want to incentivize people to correctly report their values. And then, subject to that constraint that X paired with P forms a dominant strategy truthful mechanism, the thing that we want to optimize for is our expected revenue, which we can now describe as follows. It's our expectation, now not over just one person's valuation, but over n bidders' valuations that are each drawn independently from this distribution D. And the thing that we want to maximize in expectation is the sum over all of the bidders of the payment made by each bidder I. Okay, this is going to be a function of all of the reported valuations, and that's why this payment rule takes as input the entire vector of valuations V. And there's a question, is it possible for a non-truthful mechanism to maximize revenue? Its equilibrium could be more complex to characterize, but there could be non-truthful equilibria that yield higher revenue than truthful mechanisms. Is that ever the case? So that's a good question. And amazingly, the answer is almost always no. It's sort of without loss of generality to consider truthful mechanisms. And I'll briefly describe for you like a simple form of that argument, and then just tell you the more complicated thing, but we won't go into it. So suppose I told you that I had some mechanism that had a dominant strategy for every player, but that wasn't truthful. So every player had a dominant strategy, but the dominant strategy did not necessarily correspond to their true valuation. Okay, well then I claim there's a simple simulation argument that I can use to convert that into another mechanism which gets exactly the same revenue, but now it's a dominant strategy for everyone to report truthfully. And if I can actually carry out this reduction, then there's no reason ever to consider mechanisms that have dominant strategies that aren't truthful. Okay, and what I would do is simply the following. I would take your mechanism, and then I would sort of layer on top of that what you could think of as a bidding proxy. The bidder proxy would just ask you, what is your true valuation? And then it would, in the original game, play whatever the dominant strategy was corresponding to that truthful valuation. Okay, and now, since it's acting in your interest, since it's playing as a dominant, since it is playing the action that was your dominant strategy, your dominant strategy in this new mechanism is to report truthfully. Now, more generally, it's possible to consider mechanisms that don't have dominant strategies, and we can consider what happens in equilibrium. And in a setting like this, where players have valuations drawn from distributions, the relevant kind of equilibrium is what's called a Bayes-Nash equilibrium, and we're not going to talk about it in this class. But there's a similar reduction there as well, and what it lets you derive is that without loss of generality, for whatever solution concept you're interested in, you can consider mechanisms in which people's equilibrium actions are to report truthfully. And this family of reductions is called the revelation principle in mechanism design. And so, yeah, we're not going to talk too much about this, but it's sort of the reason that we can be justified in talking about revenue optimality and only consider dominant strategy truthful mechanisms. In general, there's something called the revenue equivalence theorem that shows in more generality, you know, if I consider non-truthful mechanisms and think about their revenue in equilibrium, I cannot make more money than I would make with the optimal dominant strategy truthful mechanism. So, you know, I could consider first price auctions, I could consider second price auctions, they would tend to get the same revenue in equilibrium. So, good question. Okay, so, you know, with that justification hand waved, we can proceed to think about the problem of maximizing our expected revenue over the class of all dominant strategy truthful mechanisms. Now, because we're thinking about a single item auction, we are working in a single parameter domain. And remember this constraint that the pair X and P has to be a truthful mechanism, while in general that could be a complicated constraint. For single parameter domains, we understand this very well. In particular, there is a payment rule that makes a mechanism truthful if and only if the allocation rule is monotone, right? Monotone non-decreasing, we proved this a couple of classes ago. And in fact, if our allocation rule is monotone, then we know what the payment rule has to be. So in fact, the entire design problem is to design the allocation rule. Once the allocation rule is defined, we also know what the payment rule is, so long as it's monotone. And so that's how we're going to proceed. Right, so we know that we have to optimize over the set of monotone allocation rules. Otherwise, we won't have a dominant strategy truthful mechanism. And if we have a monotone allocation rule, we have a formula for P. Right, the payment rule looks like this. This is what we proved 2 lectures ago. Right, it's just you know, for a bidder I, it is VI, well, times their allocation. So VI times 1 if they get the item, VI times 0 if they don't, minus the integral from 0 to VI of the allocation they would have gotten had they bid Z, where Z is the variable of integration ranging from 0 to VI. So, you know, we can the way we're going to proceed is we're going to take this formula for the payment rule, we're going to plug it in to this expectation that we want to maximize, and now we will have an optimization problem defined only in terms of the allocation rule, right? So this is going to make things a lot simpler. We won't have to simultaneously optimize over X and P with some, complicated constraint relating how X and P have to interact with each other. Instead, we're going to have an optimization problem defined only in terms of our allocation rule X. Okay. So, that the expression for P, that's the payment rule if our allocation rule is monotone. And we know that if our allocation rule is not monotone, then our mechanism cannot be made dominant strategy truthful. So, how should we think about optimization here? Well, why don't we just sort of cross our fingers and hope we get lucky? Before we derive what X is, just assume that whatever X is, it's going to be monotone. So then we'll have an expression for P. Given that expression for P, we can try to figure out what is the optimal allocation rule X. And if, when solving this optimization problem, we happen to come up with a monotone allocation rule, then we'll be done. Right? We'd be in trouble if, after solving for X, X wasn't monotone. Then we'd have to work a little bit harder. But if we use our expression for our payment rule for monotone X and then optimize over X without any constraints at all, and we get lucky and X is monotone, then it will also be the solution to the constrained optimization problem where we're trying to optimize just over monotone X. Does that make sense? So we'll try to solve an unconstrained optimization problem without the constraint that X is monotone, and if we're lucky, the solution to that unconstrained optimization problem will satisfy our monotonicity constraint anyway, and that'll just make our optimization problem easier. Okay, and so let's just again sort of write down what we want to do, and I want to focus on sort of the simplest term that I can. So what we want to do is we want to, remember, maximize the expected value over a full vector of valuations drawn independently from this distribution D of the sum over all of the payments made by all of the bidders. So let me note a couple of things here. So first, expectations are linear, so I might as well take the sum outside of the expectation. And second, we're assuming that all of the valuations are drawn independently of one another, right? So bidder 1 draws his valuation, and then bidder 2 draws his valuation. He doesn't care what bidder 1's valuation is. His distribution on valuations is the same independently of what bidder 1 drew, so on and so forth. And so, by the law of iterated expectations, this expectation over all of the, all n of the valuations can be decomposed by first taking the expectation over all valuations of the n-1 bidders other than bidder I, and then within that, taking the expectation over bidder I's draw. Okay. There's nothing happening here except notationally, but what it's going to allow us to do is it's going to allow us to focus just on this very inner term, this expectation of bidder I's payment, fixing the bids of everyone else. The expectation is now just over bidder I's valuation and nothing else. And if we can derive a nice expression for this, we can just plug it in here and sum them all up. Okay, so that's what we're going to try to do. And just a little bit of notation, we're going to go through a nuanced, but not that complicated derivation on the next slide. We have this distribution D. Okay, it's a continuous distribution on valuations, let's say between 0 and 1. And so it has some probability density function. Okay, informally, this is sort of the weight, the probability density function, which I will write as little f of p is informally the weight that this distribution places on the valuation of p. And we also have the CDF of the distribution, the cumulative distribution function, which I'll write as capital F of p. And that's just the probability that a valuation drawn from this distribution is less than or equal to p. And we can relate that to the PDF, right? It's just the, what's the probability that a valuation is like less than or equal to p? Well, if it were a discrete distribution, it would just be the sum over all values less than p of the probability of those smaller values. Since it's a continuous distribution, it's just the integral over all smaller values, all of the values between 0 and p of the probability density function at those values. Okay, so this is just notation. Little f means the probability density function. Big F means the cumulative distribution function. Okay. So remember, right, due to this law of iterated expectations, we can consider just this inner term. Ultimately, we're interested in the, expected revenue, which is the expectation of the payment of all of the bidders, and the payment is a function of all of the reported bids. But we can focus in on just the expected value of the payment made by a single bidder I, and we can take this expectation only over the draw of bidder I's valuation. Right? V minus I, the bids of everyone else, will be a constant throughout this whole argument. Okay, so we want to figure out, all right, what is the expected payment that bidder I is going to make? And nothing is happening here except I'm plugging in the definition of the payment rule. This is the payment rule we derived a couple of lectures ago, okay, as a function of bidder I's valuation, VI. And it's just, well, VI times the indicator of whether bidder I gets the good minus the integral over all values smaller than VI of the indicator whether bidder I gets the good if he bids some particular smaller value Z. So this is the difference of two terms. And again, remember that expectations are linear. And so I can just consider this as the difference of two expectations. So let's do that, right? Nothing else has happened here. I've just, in going from line 1 to line 2, separately taken the expectation of the first term and the second term. Okay, and now what I want to do is I want to expand the expectation. I want to open up this term. And so what's an expectation? Well, if I'm taking the expectation over some value v, if it were a discrete distribution, I would just take the sum over all possible values v of the expression inside the expectation times the probability of that value v. And it's an expectation over a continuous random variable, and so I do the same thing, but with integrals. Okay, so the expectation of this expression, vi times xi of vi, is now just the integral over all possible values of vi. They range, remember, between 0 and 1, of the expression that I'm taking the expectation over, vi times xi of vi. And now each of the terms in the integral is multiplied by the probability density at vi, right? Informally, the probability of seeing a particular value vi. Really, it's probability density. Okay, so all that's happened here is in the left hand, for the left hand expectation, I've just written out the definition of an expectation. And I'm going to do the same thing for the right hand side. Okay, so for the right hand term, I'm also just going to now integrate over all possible values of vi, right? Remember, they range between 0 and 1, of the probability density at vi, f of vi, times the expression that I'm taking the expectation of, which is itself an integral. Okay, but this is just the expression inside the expectation. Now, on the right-hand side here, we have two integrals, right? Because there's an integral related to the expectation, and then the thing that we're taking an expectation of is also defined in terms of an integral. And I think I've already mentioned to you in this class that the first law of mathematics is that whenever you encounter two summations, you should interchange them. And that extends also to continuous mathematics. Whenever you encounter two integrals, you should interchange the order of integration. And so let's try that, right? Instead of first integrating over vi and then on the inside integrating over z, let's first integrate over z and then integrate over vi. Okay, so we have this term that used to be in the inner integral, right? It's just the allocation that you would get if you bid z. It's now in the outer integral. It's the allocation that you would get if you bid z. And z, again, can range over all possible valuations, so between 0 and 1. And, you know, okay, like these terms that showed up in the earlier double integral, xi evaluated at z, which of the f of vi terms did they get multiplied with? Well, they got multiplied with each f of vi term where vi was bigger than z, right? Because this xi of z term appeared in an integral only over values that were smaller than vi. So it gets, you know, values of z that are smaller than vi. So the z terms here get multiplied by values of vi that are larger than z. Okay, and so to make sure that we have the right expression when we swap these integrals, the inner integral, the integration over vi, now has to range from z to 1, okay, of f of vi. So there's a question, where does the assumption that x is monotone play into this? And perhaps there's even an answer. It says, we aren't assuming, we believe, we aren't assuming, we want to end up with one that is monotone, I believe. That's correct. So the assumption that x is monotone, and we're hoping that it won't end up having to be an assumption. We'll want to verify it at the end. But the assumption that x is monotone comes in the very first line, right? Because what's the right-hand side here? This is the payment rule that, when paired with a monotone allocation rule, makes a mechanism dominant strategy truthful. So in order for this to be a dominant strategy truthful mechanism with this payment rule here, x had better be a monotone allocation rule. Now, x is, of course, not something we've fixed. We're going to try to optimize over x to maximize this expression that we're deriving. And we're going to hope that when we optimize over x, we find something that is, in fact, monotone. And we haven't done that yet. So we don't know what x is yet. But we're hoping it's going to be monotone, because only if it's monotone will the first equality hold. And we're going to, you know, we have to wait and see. But when we're done with this derivation, we'll have something we can try to optimize over. Does that make sense? Great. Okay. So just to sort of recap where we are, since, you know, this isn't going to be a long argument, but, you know, easy to get lost, we just wrote out the expectation of our payment rule. Okay, and we can separately take the expectation of the first term and the expectation of the second term. Then we just expanded out the definition of an expectation by integrating over the variable we're taking the expectation of. And we found a double integral in our second term, and by the first rule of mathematics, we're required to swap the order of integration. Okay. So the next step is just a, you know, a syntactic trick. There's no actual math going on. I'm just going to rename variables. So nothing's happening in the first term. You know, I'm going to leave the first term alone for a while. But in the second term, just to sort of make the notation line up better with the expressions we have in the first term, I just want to rename my variable z as vi, and I want to rename my variable vi as z. Right? Like the value of an integral, you the integral doesn't care what you called the variable of integration, so I can rename them at will. And here, all I'm doing is wherever there was a z, I'm replacing it with a vi, and wherever there was a vi, I'm replacing it with a z. Okay, I'm just renaming things. I'm not doing any actual math. Okay. And the reason I'm renaming things is because it's going to be visually pleasing to note that we now have expressions both on the left and on the right that are of the same form, xi of vi. Okay. Okay. And what did we gain by swapping the order of integration? Well, one thing we gained is that this inner integral is now more interpretable. What is this inner integral? It's now the value of the probability density function, right? Evaluated, integrated from all values vi and larger, right? Integrated over all values that are vi or larger. So it is just the probability that a randomly drawn valuation from our distribution is larger than vi. So recognizing that, I can replace this inner integral with just 1 minus capital F of vi, 1 minus the cumulative distribution function of my distribution, right? F of vi, remember, is just the probability that a randomly drawn value is smaller than vi. And so 1 minus F of vi is just the probability that a randomly drawn value is larger than vi. Okay, that's exactly what this integral was representing. It's the probability that a randomly drawn value takes some value that is larger than vi. And now we're almost done. All that we're going to do now is combine terms. Okay, because we have now both on the left and on the right an integral over all values that vi could take of the allocation that is realized when we have value vi times something. So we can combine terms and end up with just one integral, right? It's just the integral of vi. Note that when we multiply that by the allocation rule x and the probability density function f of vi, we get exactly the expression that we're integrating on in the left, okay, minus 1 minus capital F of vi, right, the term from the right, divided by little f of vi, which is going to cancel out here. Okay, so all that's happened in going from the previous line to the next line is I've combined terms. If you expand out, if you just multiply through, then you get exactly the previous line, right? I have two integrals. They're integrating over exactly the same variable and exactly the same range, so I can consider them to be just one integral. And then I'm just combining terms. And note that this final integral is actually an expectation, right? It has the form of an expectation in that it's an integral over all possible values that vi can take of some expression of vi times the probability density of vi. Okay, so this is just an expectation. So here we're just, again, like using the definition of an expectation in the other direction, right? So this final expression is now just the expectation, again, over the random draw of bitterized valuation of this thing, right? vi times 1 minus the CDF evaluated at vi divided by the PDF at vi, okay, times bitterized allocation, okay? And what we've derived is that the expected payment made by bittereye is equal to this, is equal to the expectation of this quantity at the bottom, which depends only on the allocation and on the distribution. Okay, and so you know, we can make that even simpler by just defining some new notation. Let's write 5 vi to just equal, you know, this term that we derived on the last slide, and let's call it the virtual value. Okay, so what we proved on the last slide is that our expected revenue for a dominant strategy truthful mechanism, which is, remember, again, defined by a monotone allocation rule X and a corresponding payment rule P, you know, it can be written as this extremely simple function, right? It's just the sum over all of the bidders of the virtual value of that bidder times the allocation given to that bidder. Okay, so it's just, you know, if I give the item, for example, to bidder 5, then this this expression just evaluates to the virtual value of bidder 5. And so if you like stare at this, you'll notice that this looks just like the welfare objective, right? Like, what's the welfare objective? What's the social welfare? Well, it's just the sum over all of the buyer, it's the sum over all of the bidders, I, of the value that bidder I has times the allocation that we give to bidder I, right? It's the sum over all of the bidders, I, of their value times their allocation. Well, this is just the same thing. It's the sum over all of the bidders, I, of their virtual value times their allocation. So what we've derived is that if the thing that we want to do is maximize revenue, expected revenue over the distribution, then equivalently, we can just try to maximize virtual welfare, where virtual welfare is just welfare, except wherever bidder I's valuation would have shown up, we'll instead replace it with his virtual valuation, which is his valuation modified by some expression that depends on the distribution. And so if we want to maximize revenue, we can focus on coming up with an allocation rule that optimizes this virtual welfare. We have to optimize this in expectation. But note that certainly if we can come up with an allocation rule that optimizes this pointwise, that sort of maximizes this expression for every possible realization of the bids V, then of course we will have also optimized it in expectation. And remember that it's easy to maximize welfare pointwise. It's easy to sort of give the item, say, to the person who wants it the most. And so there's a very simple allocation rule that will maximize this, this virtual welfare. And it's going to be exactly to give it to the person who has the largest virtual value. Well, not quite, right? Because yes, certainly you'd never want to give the item to anyone except the person who had the largest virtual value. But note that although values, you know, people's values are non-negative, they're numbers between 0 and 1, the virtual values actually can be negative, right? Your virtual value is your value minus something, right? Minus something positive. So your virtual value actually might be negative. And if everybody's virtual value is negative, then the virtual welfare will also be negative if I give the item to anybody. And so the allocation rule is just a little bit more complicated. The allocation rule that's going to maximize this virtual welfare function pointwise is going to be the one that gives the item to the bidder who has the largest virtual value if it's positive, and if nobody has if nobody has a positive virtual value, if everybody's virtual value is negative, then I actually won't give the item to anybody. I'll just hold on to the item. Okay, so this is, yeah, first of all, like a slightly interesting allocation rule. It's very, very simple. And it's definitely not social welfare maximizing, right? Because sometimes I'm not giving the item to anybody, even though people have positive value for the item. I'm like, holding it, and I'm holding it exactly so that I can force people to pay me more than they might have had to otherwise in other realizations of the valuation function, right? Like remember, the VCG mechanism, if there's only one bidder, will of course always give the item to that bidder, because you have to give the item to that bidder to maximize welfare. And because it has to be dominant strategy truthful, it has no choice but to charge that bidder nothing. You can already start to see that even with a single bidder, this mechanism could hope to make some money even with a single bidder, because there's the threat that if you don't bid high enough, if your virtual value is not high enough, I won't give the item to you. Right? I can't make that threat if I have to maximize welfare. But if I don't have to maximize welfare, I can make that threat, and that threat might cause you to truthfully bid higher than zero if the risk of underbidding is that you don't get the item. And finally, right, we have to remember how we got here. We sort of said, okay, well, why don't we cross our fingers and just hope that our allocation rule is going to be monotone, and then we're going to derive the mechanism that maximizes our revenue, right, in an unconstrained way, but starting from this assumption that our allocation rule was monotone. And in order to close the loop, in order to make sure that any of this makes sense, we do have to verify now that our allocation rule is monotone. And there's a simple condition under which our allocation rule is definitely monotone. Okay, so suppose our virtual value function is monotone, right? Suppose that the larger your value is, the larger your virtual value is. Well, then for sure, this mechanism is monotone, right? What does monotonicity mean? It means that if you unilaterally raise your bid, you cannot go from winning the item to losing the item. Well, if raising your bid only raises your virtual valuation, then this mechanism satisfies this property, because by raising your virtual value, if you previously had won the item, meaning your virtual value was non-negative and you were the bidder with highest virtual value, then certainly that'll still be true if you raise your virtual value. And raising your bid will correspond to raising your virtual value exactly when this virtual value function phi is monotone. So let's just define a distribution to be regular if the virtual value function is monotone. So certainly for regular distributions, sort of, like by fiat, that's how we defined regular, this allocation rule is monotone. And so if the distribution is regular, we have now completely derived the revenue optimal auction. And that wouldn't be so interesting if there were no regular distributions, but there are plenty of regular distributions. So let's just sort of go through one example, but there's plenty of other regular distributions you can sort of work through. So again, think about, say, the uniform distribution, right? The distribution in which valuations are uniformly distributed between 0 and 1. Well, then what's the virtual valuation function? Well, remember, f of vi, the probability that a random valuation is less than vi for the uniform distribution is exactly vi. And the probability density of the uniform distribution is 1 everywhere. And so the virtual value function for the uniform distribution is just 2 times vi minus 1. It's this monotone increasing linear function of the valuations. And so indeed, the uniform distribution is regular. And just as another sanity check, let's think about what this revenue optimal auction would do in the single bidder case, the sort of simple example we used to start off the class. remember, if we only have one bidder, the VCG mechanism will give the item to that bidder and charge him nothing. And we showed that at the beginning of the class, we could do better than that, right? We could set a posted price of 1/2, and we could make $0.25 in expectation. In fact, we showed that was the best you could do over all posted price mechanisms, but maybe there's some more clever mechanism out there. And so now we have the optimal mechanism for that setting, because we have the optimal mechanism for any number of bidders. And what's the mechanism, like what is the mechanism we've just derived when there's only one bidder? Well, remember, the mechanism we derived gives the item to the person with the highest virtual valuation if it is non-negative. Well, when there's only one bidder, you're always the highest virtual valuation, and so the only thing we have to make sure is that your virtual valuation is non-negative. And for the uniform distribution, your virtual valuation is just twice your bid minus 1. And that is non-negative exactly when your bid is higher than 1/2. And so the allocation rule is just going to be that we're going to give the item to the bidder if their valuation is higher than 1/2. And of course, the payment rule that we have to use there is we have to charge them exactly $0.50 whenever we give them the item. Okay, and so we have recovered the optimal mechanism in this special case in which there's only one bidder. And in fact, we've proved that the setting a fixed price really is the optimal mechanism when there's only one bidder. Okay, and in general, right, this was for the uniform distribution, but in general, the optimal fixed price has to be the inverse of the virtual valuation function evaluated at 0. That is the bid at which your virtual valuation becomes positive. Okay, so what do these auctions actually look like, right? Like, if there's only one bidder, then the auction is just a fixed price. Well, let's think about it. So we give the item to the bidder with the highest virtual value when their virtual value is non-negative. But if we've got a regular distribution, then, right, remember, regularity means these virtual values are monotone. And so giving the item to the person who has the highest virtual value just means we give the item to the person who has the highest value. Okay, so we're giving the item still to the person who has the highest value, unless his virtual value is negative, in which case, this is sort of the only setting in which the revenue optimal auction will have an allocation rule that differs from just the regular old Vickrey auction, right? Because if we're giving the item to anybody, in either case, we're going to give the item to the person who has the highest value. And so what's the amount of money that the winner is going to have to pay? Well, this payment rule we've derived always has the following intuitive form. For any deterministic allocation rule, the amount of money you have to pay is exactly equal to the minimum bid you could have made and still won, right? Like, let's call P star your critical bid. P star is the smallest bid you could have made and still won. And right, what's that? Well, there's 2 thresholds you need to cross in order to be the winner. First, you have to be the highest bidder, so your value has to be higher than everyone else's bid. And second, your virtual value has to be non-negative, so your value also has to be higher than the inverse of your virtual value function evaluated at 0. If you bid higher than P star, then you win. And so just evaluating our payment rule, right, the winner pays his value minus the integral from the critical value to his value, and this is just the critical value. And so the payment rule is actually quite simple, right? Like, if both you and the second highest bidder have values that are have virtual values that are positive, then the payment rule is just the same as it is for the Vickrey Auction. You just pay the value of the second highest bidder. But if you are the only bidder who has positive virtual value, then you have to pay this other thing, right, which is higher than the second highest bid. It's the it's this critical value. It's this value at which your virtual value becomes positive. Right? There's this critical value, and you either pay the second highest bidder's bid or this critical value, whichever is higher. And so this is a very familiar auction format. It's just a Vickrey auction with a reserve price, right? If you've ever used eBay, you've encountered auctions like this. It's just, there's a reserve price of $10. The winning bidder, nobody wins unless they bid higher than $10, and the winning bidder pays the maximum of the second highest bid and $10. And what we've just derived is that, at least in this sort of setting in which we have bidders draw an IID from these regular distributions, that the revenue optimal auction is just this sort of simple eBay auction, just a Vickrey auction with a reserve price. And that's kind of remarkable that out of this potentially very complicated design space, at least in this simple setting, the thing that maximizes revenue has this very simple form. You can't do better than an eBay auction. Okay, so let me briefly discuss some extensions and limitations. So first of all, we just solved an unconstrained optimization problem, right? We didn't try to solve our optimization problem under the constraint that X was monotone. We just optimized virtual welfare and kind of like crossed our fingers and hoped that X was monotone. And then we sort of defined at the end a set of circumstances under which that was okay, under which X would be monotone, this regularity condition. So it turns out this exercise in only slightly modified form can be made to work even when D is arbitrary, even when D is not regular. You just have to be more careful with the optimization, because now this monotonicity constraint actually does bind. But it turns out that the optimal solution looks similar. It's, you still want to maximize sort of some notion of virtual welfare. It's just that you have to define the virtual value functions a little bit more carefully. Essentially, you need to sort of modify the virtual value function in order to make it monotone. If you also think about this a little bit more, we did require that all of the bidders have their values drawn independently. It was sort of important in our analysis that the valuations weren't correlated with one another, but we didn't actually require that all of the bidders have their valuations drawn from the same distribution, right? Everything would have gone through if the bidders had their valuations drawn from different distributions, with the one remark that if each bidder had their value drawn from a different distribution, then they would have each had their own potentially different virtual value function. And we would still have derived the form of the optimal auction. It's just that now the optimal auction would be kind of weird. The optimal auction would no longer look like, like an eBay auction if the bidders had different virtual valuation functions. For example, it may no longer be the case that the highest bidder is the winner. Okay, so we can still derive the optimal auction even when the bidders have different value distributions, but now the optimal auction doesn't look like something that people actually run. It looks like this much weirder auction in which you might not be giving the item to the high bidder anymore. Unfortunately, this derivation doesn't extend beyond single parameter domains, and in fact, revenue maximization beyond single parameter domains is very difficult. It's still an active research topic. Wait, looks like I have some questions. So can I explain the inverse of phi, and if the highest bidder doesn't win, doesn't that violate monotonicity? Yeah, so the inverse of phi the reason that's the reserve price is that's sort of the critical price at which if you bid above that price, you win, right? Because what's the allocation rule? Well, I'm going to give it to the highest bidder if their virtual value is above 0. And phi inverse of 0 is just the value at which your virtual value crosses from negative territory into positive territory. So that, the inverse of phi is just the the inverse of phi evaluated at 0 is just the sort of smallest bid you can place and still satisfy the property that your virtual value is non-negative. And so it forms the role of a reserve price. If you bid below the reserve price, you don't win the item. If you bid above the reserve price and are the high bidder, then you do win the item. And then another question, if the highest bidder doesn't win, doesn't that violate monotonicity? Not necessarily, right? Like I still have to make sure I have a monotone mechanism, but I could, for example, have a monotone mechanism in which, whatever bidder 1 reports, I throw it away and I just give it to the highest bidder amongst bidders, 2 through 10. That might, the highest bidder amongst bidder 2 through 10 it might not be the high bidder because bidder 1 might have bid a lot, but the mechanism is still monotone because bidder 1 couldn't have changed his allocation to a winning one by raising his bid. Right, so to evaluate monotonicity, we have to think about what the mechanism does for every reported valuation. Okay, but this doesn't extend beyond single parameter domains. And then sort of another problem with this, and one that we're going to address in future lectures, is that we have to know what the distribution is. Like in order to write down the revenue optimal mechanism, we need to know what the distribution is because that's going to determine what our reserve price is. And so if we don't know what the distribution is, then this isn't yet a complete solution. Okay, and let me just leave you with one more thing. So we've now talked about 2 different objectives, the revenue objective and the welfare objective, and they seem to be in conflict with one another, right? Like they're certainly in conflict with one another when we're selling to a single bidder, right? We sort of derive the optimal thing there. And if we're selling to a single bidder who has a uniform distribution over his value between 0 and 1, then if we want to maximize welfare, we've got to give him the item, right? But if we always give him the item, well, we have to use the VCG payment rule, which will charge him nothing. On the other hand, if we don't care about welfare, we care about revenue, then we can extract 25 cents from him in expectation. So maybe it seems like revenue and welfare are sort of inherently in conflict here. But let's think about what happens if instead of having 1 bidder, we have 2 bidders. So suppose we have 2 bidders and they both have value drawn uniformly between 0 and 1. Well, now we're going to start to get some revenue, right? Because we're going to give the item to the high bidder and we're going to charge him the value of the second highest bidder. And so the revenue of the Vickrey auction in this case is just going to be the expected value of the minimum of the 2 valuations. And it's pretty easy to convince yourself that for the uniform distribution, the expected value of the minimum of 2 draws is 1/3, right? 2 points on the line are going to divide the line into 3 parts, and by symmetry, the expected length of the first part is 1/3. Right. So the VCG mechanism, which maximizes welfare, when we have 2 bidders, actually makes more money than the revenue optimal auction when we only have 1 bidder. And so that's suggestive, right? Like we can make more money maximizing welfare if we have more bidders compared to, if we were maximizing revenue but with fewer bidders. And this actually extends quite generally. So here's the theorem. So suppose we're in this setting where we've got some number of bidders n, draw an IID from a regular distribution. So no matter what n is, it turns out that if we just run the Vickrey auction with one extra bidder, right? We maximize welfare not amongst n bidders, but amongst n plus 1 bidders, then actually our revenue's only going to be better than if we focus exclusively on maximizing revenue. We run the revenue optimal auction, but only with n bidders. And so what this means is that if you've got some auction, and you've got some marketplace, there's some number of participants in the marketplace, if you have a choice of where to spend your resources, either sort of tinkering with the rules of the auction to try to extract out that last bit of revenue, or trying to enlarge your market share, get just one extra user perhaps, maybe by marketing, or maybe just by making your marketplace a friendlier place to be, then you're actually better off recruiting just one extra bidder than trying to tinker with the rules of the auction. And in fact, this is a good reason to maximize welfare, because if you're maximizing welfare, you're sort of acting in the interests of the bidders. And so perhaps that's a good way to try to recruit the one extra bidder by saying, hey, I'm gonna run an auction that's not gonna try to maximize my own revenue, but it's gonna try to maximize your welfare. And it turns out that by doing that, if you successfully recruit even just one extra bidder, you're guaranteed to make more money. And it's actually not hard to see why this is the case. So the argument is short, and it'll proceed via a thought experiment. So consider the following hypothetical auction that I could run with n plus 1 bidders. Okay, first what I will do is I will run the revenue optimal auction that we just derived for the first n bidders. I'm gonna exclude from this auction bidder n plus 1. And only if the auction fails to allocate the item at all, which can definitely happen sometimes for the revenue optimal auction, right? Only in that case will it give the item to bidder n plus 1. And when it does that, it's going to do it for free, right? It's not going to charge him anything. And I want to make two simple observations. So first of all, the revenue that I get from this mechanism is exactly equal to the optimal revenue obtainable if I only had n bidders, right? Because I ran the revenue optimal auction on n bidders, and only when that auction failed to give me any revenue, when it failed to allocate the item, did I give the item to bidder n plus 1, and I didn't get any money from bidder n plus 1. And so any revenue I get is just revenue from the optimal auction on the n bidders. So the revenue that I get is exactly equal to the optimal revenue obtainable from n bidders. And also, this mechanism A always allocates the item, right? By construction. If the revenue optimal auction fails to allocate the item, then sort of by fiat, this mechanism allocates the item to bidder n plus 1. Okay. And this is also a dominant strategy truthful mechanism, right? Bidder n plus 1 has no incentive to lie, because in fact, whether he gets the item or not is entirely independent of his bid. And the first n bidders have no incentive to lie because I'm running a dominant strategy truthful mechanism on them. Okay, but I also claim that the Vickrey mechanism obtains the maximum revenue amongst all mechanisms that always allocate the item. It's not the revenue optimal mechanism, because the revenue optimal mechanism doesn't have to always allocate the item. In fact, it had better not, and that's easy to see in the single item case. But I claim that the Vickrey mechanism obtains the maximum revenue amongst all mechanisms that are constrained to have to always allocate the item. And that's also easy to see, because remember, we've already derived that for any mechanism, its expected revenue is just equal to its expected virtual welfare, right? And if we have to allocate the item, right? Then, like, we cannot do better than maximizing the quantity inside the expectation on the right-hand side pointwise, which corresponds to always giving it to the person with the highest virtual valuation, which may now be negative, but still, if I have to allocate the item, I should give it to the person who has the highest virtual valuation. And since we're assuming that our distribution is regular, right, and so our virtual value function is monotone, this just means that in order to maximize the right-hand side pointwise, again, subject to the constraint that I have to always give out the item, well, giving it to the person with the highest virtual valuation is just the same as giving it to the person with the highest valuation. And so that's the Vickrey auction, right? So the Vickrey auction with n+1 bidders obtains the highest revenue for any dominant strategy truthful mechanism that always allocates the item. And we saw on the last slide a dominant strategy truthful mechanism that always allocates the item and gets revenue exactly equal to the revenue of the revenue optimal auction with only n bidders, with one fewer bidder. And that auction wasn't the Vickrey auction. So the Vickrey auction gets higher revenue, which proves the theorem. Right, so that's a little interesting that sort of, if you think about the bidders, the number of bidders as fixed, then, you know, there is this tension between revenue and welfare. The welfare optimal mechanism is not the revenue optimal mechanism. But if you have the capacity to recruit even a tiny number of new bidders, doing so is worth more than switching from a welfare optimal mechanism to something more complicated. All right, so with that, I'll see you guys next time. I'm gonna stop the recording now, but I'll stick around for a few minutes in case there's any questions.